Did we do the unit conversion, the factor label thing last week? I don't think we did that in this class, did we? Okay. Right. So it often becomes important to convert units between one and another, right? Like, so you're measuring something in centimeters, and then you ultimately want that measurement to be in millimeters, or you have a dosage in ounces and you need to measure it in milliliters or whatever. You've probably done a lot of this kind of stuff before, just in your everyday life. We're gonna show a systematic way of doing that. Okay, and hopefully it'll work for whatever we need to do it for. So let's start with a pretty simple one. We're going to convert millimeters to centimeters, and this is maybe something you've done many times, and you know how to do it, and that's fine. I'm going to go through it as though this is brand new information, just so you can see the sequence, and then you'll see how it works when we get into more and more complicated stuff. So what we need to be able to do this is, first we need an identity. We need to know how many of one unit there are in the other. So how many millimeters are there in a centimeter? 10, yeah. So you should know that there are 10 millimeters in 1 centimeter. Okay. That's one of the objectives. Know know those 3 metric prefixes. So 10 millimeters in 1 centimeter. And we can now use that to convert from one measurement to another. So let's say that we have made a measurement of 36.8 millimeters. Okay. So since this is the metric system, it's pretty easy. You could probably do this just by moving decimal places. But we're going to treat it as though it's a more complicated one, so you can see when we get into the more complicated ones what's going on. One way that works well for a lot of people is called the factor label method. You can do whatever you want. As long as you can get the units converted properly, you do it however works for you. But this is one method that works for a lot of people, so I'm going to show you. You don't have to like it. You don't have to do it if you don't want to. In this method, what we do is we write down the initial unit that we're starting with. And then we think about how we're going to get from the initial unit to the final unit. And it may be just one step, it may be multiple steps. In this case, it's just going to be one step. And we kind of draw this thing like this, or sometimes it's done with a multiplication sign. It's really just multiplying fractions. And what we do is put the unit that we want to get rid of, the one that we're converting from, on the opposite side of the fraction, top to bottom, and the new unit that we want on the top. Now the reason for that is if you think about this as multiplying fractions, then those units on top and bottom will cancel, and we'll be left with the one on the top. The reason that we do it this way with the units first, before we write down the numbers, is the number one problem in these unit conversions is not knowing whether you should divide or whether you should multiply by something. So you know that there's 10 millimeters in a centimeter, but you don't know if you should multiply or if you should divide. So doing it this way, make sure that the units are in the right place, and you always then will do the right thing. So let me show you. Once you've got the units in the right place, you simply need to copy the numbers down from your identity. So 10 millimeters in 1 centimeter. So that goes there, and that goes there. And then to evaluate the expression, you multiply by everything on the top, and you divide by everything on the bottom. All right, so this is obviously something we could do in our heads, but let me show you what that looks like here. 36.8 times 1 divided by 10 is 3.68. So then our answer would be 3.68 centimeters. All right, so that's how that method works. If you just move decimal places or whatever, that's fine. You can do it that way. But when we talk about going in between systems, that's not going to work anymore. So let's try another example. Three 36.8 millimeters is how many inches? So now we've got a different problem. A little bit tougher problem because maybe you don't know how many millimeters are in an inch. And you don't have to, that's not one of the objectives. But it's something we can look up. So I would take my book or whatever. Okay. And I would look up, in the back cover, there's some conversion factors. And so you can see under length, it says 1 meter equals 39.4 inches. 1 inch equals 2.54 centimeters. Sadly, there is no unit conversion here for inches and millimeters. So what do we do? Yeah, we have to use an intermediate. So you look it up, would be one. But we have, if that's the only number we had, we'd have to use an intermediate to get in between them. So what I mean is, so this question is asking to convert from millimeters to inches. But we don't have a nice number that says this many millimeters and this many inches. So instead what we can do is go millimeters to centimeters, because we just did that, we know how to do that, and then centimeters to inches, because that's what we have in the book. Right? So I would, just to organize yourself, I would write down those formulas again. So 10 millimeters is 1 centimeter. And one in the book says 1 inch equals 2.54 centimeters. All right. So we can use the exact same setup to solve this. We just need an extra step. So we start with our 36.8 millimeters. And we're going to go millimeters to centimeters, which means millimeters go on the bottom and centimeters go on the top, just like we did before. And then we're going to add a second step where we go from centimeters to inches. So we're following this, millimeters to centimeters to inches, millimeters to centimeters to inches. Right? See how that works? And if you put all the units in there first, the names of the units, then there's a much better chance that you get all the numbers in the right place also. If you just think about, okay, I have to multiply by this or divide by this, it's really easy to get it turned around and multiply by the wrong thing or divide by the wrong thing. So let's try it. We're going to copy down our numbers from the identities. So 10 millimeters is 1 centimeter. 10 millimeters is 1 centimeter. And then 1 inch is 2.54 centimeters. 1 inch is 2.54 centimeters. Okay, so again, we multiply by everything on top, divide by everything on the bottom. We can ignore the ones because multiplying or dividing by 1 just gives you the same number. So 36.8 divided by 10 divided by 2.54 is 1.45 inches. All right, you can see how that works? Okay, you try one. .8 millimeters is how many yards? Actually, that one's not in here, so I'll have to look that up. Let's not do that then. I have that one. I don't have that number right away. Let's do meters. .8 millimeters is how many meters? So however you want to do that, do it. You can do it my way, you can do it your way. Whatever works.
This, do you want us to show work too?
So I don't ever care really if you show work or not. If it's an exam, you can't get partial credit if you don't show your work because I can't tell if you were almost right or not. But if you get the right answer, it doesn't matter one way or the other. So I think it's worth working through it just to show that you can work through it. But if you can just sort of see it, especially for a somewhat simpler one like this, then you can just do it however you want to do it. All right, so hopefully you figured out that there are 1,000 millimeters in 1 meter. That's another one from the list. So that means we can just do this in one step. Something like that. Yeah? Okay. So you'll get to practice this a little bit more in the homework. There's plenty of good problems on this kind of stuff in the book. And if you haven't ever done this before and this is like blowing your mind, come talk to me sometime and we can work out through a little bit more. We're not going to do this a whole lot this semester. It's not going to be a huge part of the class, but it is something that'll come up, and so it's something that's worth practicing and knowing how to do. And we'll do a little bit more of it when we get into chemical equations. So we will practice this a little bit more now, but let's look at one more concept first, and that is density. So what is density? Probably looked at it a little bit in your pre-lab for this week, maybe. Can we have a good definition? Yeah, go ahead.
The ratio of mass to volume.
The ratio of mass to volume. Yep, that's correct. Can anybody rephrase that in a way that tells us more about like what it means? Like, what is density? What does it mean? You want to give it a try? I thought it looked like you were going to talk about. Like, what does density tell us?
The weight.
Yeah, it's related to the weight, so it's not just the weight, because weight is weight. It's mass divided by volume. Everybody likes these math explanations. That's great. That's what we're going to do with it. But what does that mean? What does the ratio of mass to volume tell us about the thing? Maybe, yes, that can be part of it, but buoyancy has to do with more than just density, right? Because like a metal boat is still buoyant because of its shape and whatever. But you're on the right track. Yeah.
Go
ahead.
like how much there is of something in a thing.
Yes, that's exactly it. Yeah, how much there is of something in a thing. How much mass there is in a certain amount of space. That's really what the density is telling us. So it's not just how much mass there is, because you can always just get a bigger thing and have more mass. It's how much mass takes up a particular given amount of space. So that's density. We can define it as the amount of matter in a given amount of space. So the amount of matter is the mass, and the given amount of space is a particular volume. Now there's all different, because that's a pretty general definition, there's lots of different ways to express density. You just need some way to measure matter and then some way to measure space, and you take a ratio of those two. So when we calculate density, we simply need to divide mass of an object by its volume, which is what we're going to be doing in various ways today in lab. Mass we can measure pretty easily usually by putting something on a balance. Volume can be difficult to measure depending on what kind of a shape of an object you have. Some objects are easy to measure volume, others aren't. We're going to use a couple different methods of measuring volume today, both directly with a ruler and through displacement, through how much water it displaces. And there are lots of units you can use here, but we will usually use units of grams per milliliter or grams per cubic centimeter. A cubic centimeter is the same as a millimeter, so a cube that's a centimeter on each side, that's the same volume as a millimeter. So that means that to find volume, we'll generally want to find a mass in grams and a volume in milliliters and divide those two. It doesn't mean you have to do it that way. You could have a density in grams per liter or pounds per gallon or whatever. But this is just for the quantities that we use and the things that we use. This is nice and convenient. The other thing that makes this nice and convenient is that the density of pure water is, you know, you want to take a guess? Yeah, 1. The density of pure water is 1 gram per milliliter. And I'm not giving more significant figures because it actually changes a little bit with temperature. So depending on the temperature, it could be like 1.001 or 0.9998, that kind of thing. But it's about 1. So that's a nice even number. And that tells us a couple things. Mainly, it tells us that, hold on here, 1 milliliter of water weighs 1 gram. That's what that unit tells us. And that means that we can use density as a type of a conversion factor in the types of problems like we just did. So we can write that, like for water, it's 1 gram per 1 milliliter. So if you wanted to know how much a given amount of water weighs, you measure it in milliliters, you also know how many grams that is. If you measure it in grams, you also know how many milliliters it is. That's really convenient for a lot of things, for calibrating instruments, for maybe like you have a syringe that you want to use, but you actually want to measure a mass in that syringe. And so if you're using water, those will go 1 to 1. I did this, what was this? Oh, well, it was a long time ago when my kids were really little. My parents gave us an old medicine spoon that I used when I was little, and it was like shaped like an alligator. Like you put the, anyway, that's not important. But I was like, okay, that's really nice, but I have no idea if this is actually an accurate measuring spoon or not, because who knows for the quality control on plastic alligator-shaped measuring spoons back when I was little. So to figure that out, I just put it on a balance, and I put water in it until it was at 1 gram, or I think I did 5 grams actually. So and then I looked at it and said, okay, was it 5 milliliters when I put in 5 grams? And it was. So I could say, okay, that's That's probably about right. So I don't know if that's kind of a nerdy thing to do, but it worked, and we figured it out. So we used the alligator spoon. All right, let's take a look at density of other objects then. Where's my, there we go. New book, I always forget where everything is now. Okay, page 31, I was close. Okay. All right, so here's a neat picture of a few things all together. You've got some wood, water, brass, and mercury, and cork. I think cork is the wood, yeah. So the water is here in the middle with a density of 1. And we can say some things about the densities of the other materials just by what's happening to them in this beaker. So if the water density is 1 gram per milliliter, what would we say about the density of the brass? It has a higher density because it's sinking, right? It's going down in the water. So we would say that that brass has a greater density than 1. It's like a game now. Oh, okay. And what would we say about the cork? Everybody see that? So the cork's density would be less than 1 gram per milliliter because it's floating in there. And mercury is down here. That is mercury, liquid mercury, which goes down below the water, which is much more dense. Much greater than 1. The density of mercury is 13.6. We could look that up. Grams per milliliter. So the other thing we can see here is that the brass washer sinks in the water, but floats on the mercury. So that tells us that it has a greater density than water, but a lower density than mercury. So that density is between 1 and 13.6. It's not shown here, but yeah, I don't know what it is, but it's somewhere in between those. So that's how we can see the density actually happening. There aren't really good rules of thumb as to what has a greater or lower density than anything else. Some common things that you might see that you might want to know the density for. Most organic compounds, like organic solvents, oils, solvents, that kind of stuff, those are going to be less dense than water. So you're looking at things like methanol, ethanol, gasoline, vegetable oil, kerosene. That kind of stuff is all going to be generally less dense than water. And then most metals are more dense than water. So some metal objects more. Something like cork or like wood, wood can have a pretty big range of densities. And that has less to do with the chemical structure and more to do with the physical structure of how much air is actually in there, the way that the tree grows or something. So that's density. One other kind of common misconception about density is not the same as the intermolecular forces, the things that hold the molecules together. So for instance, if you see oil and water, right? The oil goes on top of the water because it's less dense than the water. But the fact that they don't mix together has nothing to do with density. That's a totally different concept. The fact that the oil's on top is because it's less dense. But the fact that they don't mix together is something totally different. Sometimes, if there's a big enough difference in density, you can actually layer things on top of each other, even if they mix. So one example is ethanol and water. Ethanol is less dense than water. And if you're really, but ethanol and water will mix together and just stay in solution. But if you're really, really careful, you can carefully layer the ethanol on top of the water and actually have it stay like that. You can see that sometimes with like alcoholic drinks because that's the alcohol that we drink. But if you like color them, you can make them like layered on top of each other, and then you can put some sort of syrupy thing on the bottom. And that's because even though all that stuff mixes together, if the difference in density is great enough, you can carefully keep them separated temporarily. All right, so let's look at how we could do a calculation with density besides just calculating the density itself. What is the volume in milliliters of a liquid that has a density of 1.20 grams per milliliter? This is exactly the same type of a problem as we did before, but instead of dealing with two of the same types of measurement, like two length measurements, like milliliters and meters, or millimeters and meters, we're dealing with a volume and a mass, so two different measurements, grams and milliliters. And normally we would not be able to convert milliliters into grams or grams into milliliters. Oh, I've left out a thing here. Hold on. We don't have enough information yet. We need the mass as well. We'll say 5 grams. What is the volume in milliliters of a liquid that has a density? Yeah, that makes sense. So when you see problems like this, where you're using the density to help calculate something else, you can think of the density as a sort of like inequality. And I'm going to put quotes around it because it's not exactly an equality, but you can think of this as meaning 1.2 grams equals 1 milliliter. That's kind of what the density means in this case. It's a way of saying how many grams are in a milliliter. So it's not exactly an equality, but we can think of it that way and use it that way. So once we have that, we can set up a conversion problem in the exact same way that we did before. Oops, sorry about that. So we've got 5 grams, and we want to convert the 5 grams from grams to milliliters because we're being asked about milliliters. But we need to fill in those numbers from a conversion factor, and the conversion factor here is the density. So the 1.2 goes with the grams, and the 1 goes with the milliliters. And then we can solve that. .17 grams. Or I'm sorry, milliliters. Sorry. Grams cancel here, and we're left with milliliters. So doing it in that way and thinking of it as a conversion problem and just following the units makes it a lot more likely that you'll get everything in the right spot, because the alternative is to say, okay, I know I've got a 5 and a 1.2. Do I divide them or do I multiply them or what do I do? And you don't have as good of a chance of getting it right that way. If you follow the units, there's a better chance everything ends up in the right spot. Let's try another one. If I can find the one I was looking for. what is the mass in grams of a piece of iron that has a volume of 150 milliliters and a density of 7.2 grams per milliliter. So a similar question, but now we're asking about the mass instead of the volume. So the volume is given, and we're asking about the mass. So use the same or a similar technique and see if you can get that converted. Remember to follow the units. So we set something up like this. Hopefully set something up like that. And now we have to get the numbers in there in the right place. So we've got 7.2 grams per milliliter. And we have to remember that that means something like 7.2 grams of iron equals 1 milliliter of iron. So that tells us that the 7.2 goes with the grams and the 1 goes with the milliliters. We multiply by things on top and divide by things on the bottom. And we get 1,080 grams of iron. So you think you can do that? Maybe? It's going to take some practice. You can go back and review this. But as you work through your homework, hopefully you can get it. All right, that kind of catches us up from last week. So let's get into the stuff that you've been working on in your homework on the system, which is atomic structure.
What is that?
Iron. Sorry, I should have put that over here. It's the chemical symbol for iron.
We're gonna learn the symbols again.
I mean, you don't have to know them, like, you don't have to memorize them. We've got periodic tables up here if you ever need them that have the names and stuff on the back. Or if you have one in your book or your phone or a notebook or something, you can use that too. You won't have to like memorize those symbols. You'll probably find that as you work through the class, that by the time we get to somewhere in the semester, you just like know a bunch of them because we've been using them a bunch, but you don't have to like work to memorize them. Let's talk about atoms. So what are atoms made out of? Protons, neutrons, and electrons. Yep. What is the difference between those things?
One is
Yeah. Protons are positive,
electrons.
electrons negative. No charge. Very good. Okay. So we've got protons, electrons, and neutrons, which have no charge. And where are they in the atom?
Well, the protons are in the center.
Yeah, the protons and neutrons are in the center. And what is that center called? Right, the nucleus. The protons and neutrons are in the nucleus, and the electrons out of the nucleus. The protons and neutrons make up most of the mass of the atom. Electrons are super, super tiny compared to protons. All right, so now let's think about how we know how many of these particles are in various atoms. So there's a few different ways that we can express atoms if we want to really specify how many particles are in the atom, what kind of an atom it is. So for example, let's take a fluorine atom. F is the symbol for fluorine. And we can write that a few different ways, but one way we can write it is to put a 9 here and a 19 there. And that gives us some specific information about that particular fluorine atom. So as you probably saw in your pre-reading, what does that 9 mean? Yeah, that's the atomic number. And what does it refer to? 9 what? 9 protons, right. So that means that this atom is going to have 9 protons. And those 9 protons identify that atom as fluorine. So you'll notice that on the periodic table, every different element has a different atomic number. So the atomic number is unique to each individual element. And if that atomic number changes, the identity of the element changes too. So if you take an atom with 9 protons and you add 1 more proton, you don't have fluorine anymore, you have neon. So that's the identity of the element. All right, what is this number up here? Yeah, we have to be careful with this one. This is called the mass number. And what does it tell us? Not electrons. Protons and neutrons together. So the mass number is the protons and the neutrons. And this can be a little tricky for a couple reasons. One, because the bottom number is protons, everybody always wants the top number to be neutrons, and that's not what it is. It's both of them together. So just, I don't know, whatever you have to do to remember that, it's not just the neutrons, it's both of them together. The second thing that's tricky is this is not the number that is in red on the periodic table. That is a different number. We'll talk about that number in a little bit. But that is not the same as this mass number that you would write on a symbol like that. For fluorine, it happens to be pretty close, basically the same, but that's not going to be the case for a lot of other ones that we do. So don't get that confused with the red number on the periodic table. Once we have those two numbers, we should be able to figure out all the particles because there's only one that we haven't listed here, which is electrons. How do we figure out the number of electrons? Why? Yeah, so this thing is not a charged particle. We'll talk about charged particles called ions later. This is not charged. And so that means that there has to be the same number of negative and positively charged particles so that it all ends up canceling out and becoming neutral. So in this case, because there's no charge, we can assume that we have the same number of electrons as protons. So that the two charges balance, the positive and negative charges balance each other out. Yep. The new, because they're new. So the last, I don't know, what is that, 9 of them or so, have been discovered relatively recently and named and added to the periodic table relatively recently. These super heavy elements are discovered in these huge super colliders where they basically just like banging atoms together at super, super high speeds. And they exist for tiny, tiny, tiny fractions of a second. So there's often not enough time to actually measure them. I believe the masses are known for the particles that are measured. You'll notice they have the most in common with all the other elements that have the outlines. See how they're like outlined kind of? Those are all radioactive, which means that the nucleus breaks down over time. And so the atomic mass on those, in parentheses, is, I believe, for most periodic tables, it's the most stable version of it. The one that sticks around for the longest, but ultimately it's going to break down and form other stuff too. So I don't know if those aren't known or if they just weren't added to the table yet. I don't know. Okay. So the other thing that we should know is there's a couple other ways that we could write this symbol without losing any information. And that is like this. We could write 19F like this without writing the lower number. Why haven't we lost any information if we don't write that lower number? Why don't we need that? Why don't we need the lower bottom number? Yeah, because fluorine always has the same atomic number, which is 9. And you can look it up on a table. I mean, if you didn't have a periodic table, then you would need that. But you know, we're always here. There's always a periodic table. So we can always look up fluorine and know that it goes with 9 protons. 9 protons means fluorine. Fluorine means 9 protons. It's right there on the periodic table. So we haven't lost any information there. And so this is more commonly how these things are drawn. Also, sometimes it's written like this. Fluorine 19. We do need to specify that 19 because there could be different other types of fluorine, fluorine 18, fluorine 20, whatever, that have different numbers of neutrons. But as long as we have that 19 there, we have all the information that we need. We're going to define one word here, isotopes. Isotopes are atoms that are the same element, so the same number of protons, but a different number of neutrons. Most elements have different isotopes that are that exist in the world. So for instance, carbon has 3 isotopes: carbon 12, carbon 13, and carbon 14. How many protons are in carbon 12? There's 6 protons. And how many protons are in carbon-13? Does everybody see how it's the same? It's still carbon, and carbon always has 6 protons. So all of those are going to have 6 protons. All right. So then how many neutrons are in carbon-12? 6, because it has to add up to 12. And what about carbon-13? 7. Carbon-14? 8. Okay. Whoops, not electrons, neutrons. So same number of protons, different number of neutrons, we get these isotopes. And this is where this red number comes in. So each of these isotopes has that specific mass number, either 12, 13, or 14. But if you look up on the periodic table at carbon, which is number 6, you see that its red number is 12.011. So let's actually draw that so we don't get confused here. So we've got carbon, and we've got the 6 up here, and then it says 12.011. We know that this is the atomic number. And this one, the most important part of this is it is not the mass number. This is a weighted average of the isotopes. And the book actually goes through how you do that calculation and everything. We're not going to worry about that for this class. But you can take carbon, and all the carbon in the world is made up of carbon 12, 13, and 14. The vast majority of it, about 99% of it, is carbon 12. But then a little less than 1% of it is carbon 13, and then there's a tiny bit that's carbon 14. So in any given sample of carbon, unless it's an actual individual atom, it's going to have the same kind of ratio of composition of the different isotopes. So mostly carbon 12, a little bit of carbon 13, a tiny bit of carbon 14. So that 12.011 number reflects that. It's an average of all the carbon that exists in those ratios, and that's why it's close to 12, because most of the carbon is carbon 12. But if we're talking about an individual atom or an individual isotope, an individual set of atoms that all have the same mass number, we need to actually specify the mass number by giving that number, putting that number on the letter like that and saying, no, we're only talking about carbon 12, carbon with 6 neutrons. Or we're only talking about carbon 13, carbon with 7 neutrons. So if you see that little symbol with a number to the left, or you see this written like this is the mass number that tells you exactly the number of protons and neutrons. You cannot get that information from the periodic table. That is not the mass number. All right. So let's try one. I'm going to write a table. I want you to write. I'm going to leave some blanks here in my table, and I want you to fill it in. If you have a periodic table, go ahead and pull it up. If not, you might be able to figure it out. So we want the symbol, the name, the atomic number, the mass number, and then the number of each of those particles. Protons, neutrons, and electrons. All right, so first we're going to go with (81Br). So then you can fill in the rest of those blanks. And then for the second row, I'll give you some numbers and you fill in the rest of the blanks. So see if you can fill in those blanks. Once you got some numbers, talk to the people around you, see if you all come up with some of the same things, and then talk about where you had some differences. So given the symbol, write the name, number, mass number. From the information given. You may need to look up the name. Get everything from that. If you need the name. All right, got some numbers? How do you feel about your numbers? Think they're right? Maybe? Maybe close? All right, let's see. So the first one, you may have had to look up the name since that periodic table doesn't have names on it. But this one is bromine. And its atomic number is 35. What's its mass number? 81, right? Because remember, we just said that red number on the periodic table is not the mass number. The mass number is specified here in that upper left-hand corner when we write the symbol. It's 81. So that means we've got 35 protons, which we get from the atomic number. And how do we get the number of neutrons? Yeah, we're going to subtract from the mass number. So we've got, so what does that come out with? 46, right? So 46 neutrons, because the protons and the neutrons together give us the mass number. And then the electrons, because it's neutral, we've got 35 electrons. We'll talk about ions another time. All right, so the bottom one, we're not given any symbol or name. We have to come up with that. We are given some numbers. So if we've got 17 protons, 20 neutrons, 17 electrons, what's the atomic number? 17, because that always comes from the protons. And what's the mass number? 37, because that's the sum of the two. And then we've got a name and a symbol, which we can now look up, because we know 17 is chlorine, Cl. So we can write chlorine. And then our symbol is the mass number and the element symbol, 37Cl. All good? Okay. So that's it for the atomic structure in terms of the protons, neutrons, and electrons. That's all you have to be able to do, is figure out what those numbers are based on the information given. Then the next part we're going to look at is the electronic structure. What are the electrons doing? So we know that the protons and neutrons are in the nucleus, and the electrons are not in the nucleus. They are around the outside. Where they are specifically is actually a hard thing to answer. We know that they are not in specific orbits. So this idea that electrons orbit the nucleus the way that planets orbit the sun, we know that's not right. They don't quite do that. But they do exist in these kind of spherical, what we call shells, at different distances from the nucleus. So that's going to kind of dictate our electronic structure. So the electrons exist in discrete levels, which we'll call shells. Where each additional shell is farther from the nucleus and at higher energy. I know that sounds really weird. Let's show what that means. So the way I like to think about this is kind of on a graph where we have energy on the y-axis. So anything higher up is going to be higher energy. And we can talk about the level or the shell on the x-axis, and we can split this up into 3. There are more than 3, but for this class, we're just going to focus on the first 3 because it gets a lot trickier after that. So what we're going to say is that each of these levels can hold a specific number of electrons. And depending on how many electrons a given atom has, it will either have some of these levels filled or empty or partially filled, just depending on how it all works out. So I've had good luck in the past with thinking of these as little buckets because we talk about them as holding a certain number of electrons. A bucket holds things, so that might make sense. So there's our first bucket, our second bucket, and our third bucket. I've drawn them a little bit different size because the first bucket only holds 2 electrons, whereas the other 2, we're going to say, holds 8. Now, if you've taken some chemistry before or you were reading some other stuff, you may know that the third one actually holds 18, but we're not going to get into why that is or what's happening there. So for our purposes, it's going to work for our models if we say 2, 8, and 8. We've got 2 in the first, and then 8 in each of the second, or in the second and third. So the way we use this is we figure out how many electrons are in a given atom, and then we fill up the buckets, and then we know some things about where those electrons are in a given atom. So for example, let's take sodium, which is Na, and we can make its electron configuration by putting its electrons in these buckets in these different energy levels. How many electrons does a neutral sodium atom have? Let me see. 11. You can look it up on the periodic table. It's 11 protons, so it's got to have 11 neutrons or 11 electrons if it's going to be neutral. So we've got 11 electrons to put in these buckets. Remember, the first one holds 2, then the second one holds 8, and then the third one holds 8. So we're going to just count them out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now we've got 8 in there, so that's full. So that 11th one has to go up here. That's not too hard, right? That's it. That's the electron configuration for sodium as far as we need to know it. This tells us that there are 2 electrons in the first energy level, 8 in the second level, and then 1 in the third level. And then we have a couple special names for those. The highest level that contains electrons is called the valence shell. And those electrons are called the valence electrons. Why do you think those might be important? Why do we care about having a special name for the higher outermost electrons? The electrons that are furthest from the nucleus at the highest energy. Yeah.
They're the ones that are going to.
Yeah, they're the ones that are going to do stuff. Did you want to add to that?
Yeah.
You're going to say something? Yeah. Those are the ones that do stuff. All the other electrons are kind of protected because they're being attracted to the nucleus very strongly. The ones that are in the outermost level are the ones that are the most free from the nucleus to go do stuff. So by do stuff, I mean they can get transferred to other atoms. They can accept electrons from other atoms. They can connect and bond with other atoms. So those electrons are going to be the most important. So in this case, which shell is the valence shell for sodium? Yeah, so for sodium, level 3 is the valence. And another thing we could say about that is sodium has 1 valence electron. That's another thing we could say. Because there is 1 electron in the valence shell, sodium has 1 valence electron.
Isn't there like a different way to drawing the circles out?
Yep, there's another way to do it with drawing circles. If you like that better,
Yeah.
that's fine. Yep. Yeah.
We have to know that.
No. You don't have to know that stuff. Yeah, so within the shells, we can actually separate this into even these sublevels that are called S and P and D and some other stuff. We're not going to get into that in this class, so you can ignore that part for now. All right, let's see, we got about 5 more minutes. Okay, so with our last 5 minutes, I want you to try to do the configuration for lithium, Li. So do the same thing. Draw either buckets or circles, whatever you like, and determine what is the valence shell and how many valence electrons does it have. Should be fairly quick because there's not too many electrons there. No, because it depends on how many electrons. This one won't have any in the third. Yep, because the valence is the highest level that contains electrons. So it would be the second one. Yeah. So if we put those in here, we go 1, 2, 3. And because that's all the electrons, just 3 of them. So in lithium's case, the valence shell is number 2. And we can say that it has 1 valence electron. All right. So let's compare lithium and sodium now. So sodium, the valence was level 3, and it had 1 valence electron. Lithium, the valence shell is number 2, and it had 1 valence electron. In fact, let me move this up so we can see that. Now, take a look at the periodic table and the position of lithium and sodium. So lithium and sodium are in the same column, right? Or group sometimes, we'd say, or family. And which group is that? They have labels on the top. So they're in group 1A, and they each have 1 valence electron. So is that a coincidence? It's not. It's kind of set up that way. So for all the columns except the middle, the B's, but all the A columns, the column number actually corresponds to its number of valence electrons. Because imagine, okay, we just did the one for lithium. What if we were to do the one for beryllium, Be, which is right next to it? All we have to do is add 1 more electron, and it would go in the second bucket, right? And so then that would have 2 valence electrons, and it's in column 2. You can also tell which bucket is the valence bucket, or which level is the valence shell, by the row that they're in. So notice that lithium is in row 2, and its valence shell was number 2. Sodium is in row 3, and its valence shell was number 3. That's not a coincidence either. So you can see in the structure of the periodic table, in the first 3 rows, the first 3 periods, the first one has 2 atoms, just like the first level only holds 2 electrons. The second row has 8, just like the second level has 8 electrons, or can hold 8 electrons. And then the third one has 8, which can also hold 8 electrons. So you should be able to answer these questions, or we should be able to answer these questions without even doing the buckets, just by looking at the periodic table. So if I said, all right, let's do the same questions with sulfur, S. We can look at its position at the periodic table. Does everybody find it? S? We see S? So which level is going to be the valence shell for S? It would be 3, right? Because it's in the third row. So the third bucket is going to be its valence. And how many valence electrons will it have? 6, because it's in the 6th group over. So just by looking at the periodic table, we can do this without having to fill in and count all the buckets or the circles or whatever. That's why it's set up like that. All right, questions about that? So we did atomic structure, we did electronic structure. On Thursday, we will look at matter and start talking about ions. Our first quiz will be a week from today on Tuesday. I think on Thursday, depending on how much time we have, we might just do it as a take-home thing, but I want to do a practice quiz just to kind of try out the system and make sure that everything's working, and so you get a sense of what a quiz is going to be like before we do a real one that counts. So the first real one that counts will be a week from today.
All online?
They're all online, but we're going to do them in class. All right, so we'll be back in here for 15 minutes to start lab. Yeah. Yes. You can still do them, you know, you just rotate back. What? The group tells you the number of electrons. And the period tells you which level is it. Which level.
So I did that too. I wasn't. That's fine.
Oh, the homework for a couple of days?
Yeah.
Okay. Yeah, so if you are
So it's like
behind on the homework.
every new chapter you have to do that?
Maybe.
Like every new chapter, it's a new thing.
Yes, there's going to be a new thing. And then there's also going to be a set of practice problems for after we do it. So you'll notice there's another assignment due on, I think, Saturday. On the 1st?
On the 31st.
31st. Yeah.
The
problem, that's the problem, the practice problems. Yeah. And so if you get behind on those or you missed a couple, just let me know. I can set the dates back. As long as it's not every single time where it gets to be really challenging, I'm happy to see that. Yeah.
Like there was one question which said that if you get a burn, there are 3 options. So I tried all 3 of them, and it's still saying that I'm wrong.
Yeah,
so like
we changed that question. So
like first you would notify the instruction you, and then wash your hands and